Welcome to Lecture 2.4, the four subspaces. Over several upcoming lectures, we will learn about the transpose of a linear map and then how to encode an arbitrary linear map with a matrix. Though it is certainly not necessary, it is helpful to have some familiarity with undergraduate level matrix analysis or linear algebra before seeing these. It helps give some context so we sort of know where we're going. It's like having training wheels. Otherwise, some of the results that we see are not going to make any sense without the context. In this lecture, we will review the four subspaces that arise from every matrix: the column space, the row space, the null space, and the left null space. Even though we have not seen matrices so far in this series of lectures, it is assumed that you have taken an undergraduate linear algebra course, or at least are familiar with those topics. Now, not every undergraduate linear algebra course is going to present these four subspaces in the way that I will. This is motivated by Gil Strang's excellent book on linear algebra. Now, you probably have heard of the column and the row space, and certainly the null space. The left null space is maybe less common, but these four subspaces are all very related to each other. And when we see future results about the transpose of a linear map and encoding linear maps with matrices, it will really help to understand how these four subspaces are tied together. In other words, they will motivate the more theoretical concepts and results as they arise and will give them context. Now, it is certainly not required that you view this lecture. This lecture can be seen as optional, but I strongly recommend it because I think it'll help make the remaining lectures in this section make more sense. Throughout this lecture and the following, we strongly recommend viewing vectors as column vectors and scalar functions as row vectors. Okay, let's get started. Throughout this lecture and beyond, we will let A be a linear map from Rn to Rm, though really it works just as fine if we have the complex numbers here or even a finite field. But we usually work with real value matrices anyways, so let's stick with this. And we can think of this as an m by n matrix, and sometimes we write that as putting parentheses around Aij. Now, it's so easy to get confused as to which one is m and which one is n. Is that rows or columns? So here's how I think about it. So if A is a matrix like this, I'll draw it so it's definitely not square. And then if this is going from Rn to Rm, that means that the input vectors must be so the input vectors is the size of the number of columns. So in other words, this is, so there are n columns here, and then of course that means there has to be m rows here, and so this is in Rn, and this is Rm. So we say that this is an m by n matrix. Here's how I always think about this. So I make an L, I do m times n. So m of these, n of these, that's where this m by n comes from. And that is going to be the opposite of n, Rn to Rm. The transpose of A is a linear map from Rm to Rn, and we can think of this as an n by m matrix. Now, I haven't defined transpose, but again, this is one of those things that you should have seen in undergraduate linear algebra. If this is A, which is m by n, then A transpose is what you get by swapping rows and columns. So it will look like this. It'll be n times m. Now, this is a map from Rn to Rm, because again, you take an n vector and you get an m vector. Now, a transpose, this goes from Rm, and then what you get out is a vector in Rn. Now, these are not inverse maps of each other. But another way that I want to emphasize throughout this lecture and beyond is that another way to think about a transpose, instead of taking, let's say, this vector, so this is a transpose and this is some vector x, I want you to think about taking this original matrix A and multiplying it by the transpose of this vector on the left. So in other words, x, so let me call this x transpose here. So this vector, so if we do this, what we will get is we will get a vector that is 1 times n. And again, if you forget this, remember, draw the L, n by 1 by n. So if we multiply this, we're going to get a vector, let's call it u transpose here. And this row vector is the transpose of this column vector here. So instead of thinking about taking the transpose of matrices and multiplying them by vectors, we can think of taking the regular matrix and multiplying them by row vectors on the left. It's really the same thing. Okay, so for any matrix A, the range of A as a linear map is the span of the column vectors, which is called the column space of A. So this is something that you should remember from your undergraduate days, that if you have a matrix A and then it's got a bunch of columns, well, let's suppose that you have a basis x1 up to, actually, how about if I call it e1 up to en? That's typically the basis that we use. Then these columns literally are AE1, AE2, AEN. And we'll talk more about this in a couple lectures when we encode matrices with, or we encode linear maps with matrices. But what this means is that if we have this, say that this is like E1, this is E2, and this is E3, and then we apply A, whatever the heck we get, this is AE1, this is AE2, and maybe AE3 is here. I'll let you think about whether in your head this is a plane or whether this is R3. This is the range of A. So the subspace spanned by the columns, all linear combinations of the columns, is the range. And we call that the column space. And the dimension of this is called the column rank of A. Now, the range of the transpose of A is, so if you take A and you turn it on its side, so if I had here, if I take a transpose, then the span of the column vectors of this is equivalently, you can think of as the span of the rows of A. So we call that the row space, and the dimension of the subspace spanned by the row vectors, or equivalently the column vectors of the transpose. Again, these are just n tuples. These live in some n-dimensional space. It's called the row rank. It's a fundamental theorem that we will prove in more generality in a few lectures, that the dimension of the range of A and the range of A transpose are the same. So because of that, the column rank and the row rank are the same, which means we can give it a more general name and just call it the rank of A. Now, remember, the range of A is a subspace of R. Again, if we're going from Rn to Rm, lives in Rm, and it is a span of, and it is a span of n vectors in Rm, and the range of A transpose lives in Rn, and this is a span of m vectors. So it seems to be a minor miracle that we have a different number of vectors living in a different dimension of space, but they always end up to be the same dimension. Moreover, if you take the matrix A and you restrict it to the range of the transpose, then it's a bijection on the subspace. It maps the range of A transpose to the range of A. This is something that certainly is in any undergraduate linear algebra textbook, but I think it's one of those details that is often not emphasized. A lot of linear algebra classes intro classes. They don't do vector spaces till near the end of the course, like page 250. And so a lot of stuff is thrown in. And this is one of those details that is not emphasized that much, so it's often glossed over. But it's important, and I'll show you in the next slide especially how these two subspaces relate to each other and how these relate to the null space and the so-called left null space. On this slide, I'm going to draw a picture of these four subspaces, and there's no more typed text, so it's all going to be handwritten from here on out, or at least on this slide. So what we have a linear map which goes from Rn to Rm. And now I'm going to think of this as x and think of this as u, because later in this class we're going to think of these as between subspaces, not necessarily r to the n. Now, in here, in Rn, let's think about what lives in here. So the row space lives in Rn. So this is the range of A transpose, and also the null space lives in here as well, the null space NA. Now over in the right-hand side lives the column space, so the column space, or just the range of the range of A. Now some books will call row space and column space, they'll say things like row space of A, or the row space of A, or the column space of A, or the column space of A. I like to just use this. First of all, row. This looks like the range of A, and that's not what this is at all. So I like to use this notation. I also like to use notation that, or the sort of picture that I'm going to show you now, which is due, as far as I know, is due to Gil Strang. He's the one that came up with this cartoon to visualize like 8-dimensional subspaces. This is from his wonderful book. And he also has a very nice set of YouTube lectures that are on the MIT OpenCourseWare website, and advanced undergraduate linear algebra. It's an introductory linear algebra course, but it's at MIT, so it's still somewhat advanced. So here he draws the row space like this. So it's just a rectangle, but you should think of this as like some, I don't know, 8-dimensional space or something. So let me write down that this is the range of A transpose. So this is the row space, or the column space, the range of A transpose. And this is going to have, let's say that it is R dimensional, for where R is the rank. So let me write down row space. And then one big idea is that A, when restricted to this space, is a bijection. So in other words, if we apply A, then we map onto the column space. This is the range of A. So this is also a R-dimensional subspace. Here we are living in Rm. Here we are living in Rn. So this is R-dimensional. This is called the column space. And once again, this is the zero vector. Now the null space also lives in here, and I'll draw that as something like this. So this is the null space of A, and this is n minus r dimensional. So it's something that I don't think we've proven yet, although we will definitely do it when we talk about transpose, is that so in Rn, these two things are subspace complements. So let me write down, this is the null space, and Rn is equal to the range, or the direct sum of the row space and the null space. So again, I'm not proving this. We could prove this in this context, but I think we'll prove it more generally in the next few lectures. So it's also not hard to show that vectors in the null space have to be orthogonal to vectors in the row space. Now, I have not also defined orthogonality, but I hope you have seen that in your undergraduate class, so you know what that means. So basically it means perpendicular, and so one way to think about this is that means every vector in here, x, can be written as something in the row space plus something in the null space uniquely. So it can be decomposed as how do I want to say this, as x, I don't know, x1 plus x2, where these things are perpendicular. Now, it's not hard to see why this is the case, why these things are perpendicular. Like, let's think about what it means to be in the null space of A. So I will go up here. Let's suppose A is something like this. If A is in the null space, that just means that A times X is the 0 vector, which means that every single individual row times X has to be 0. And that's exactly what it means for these row vectors to be perpendicular to this column vector, is that their product, which is just a dot product, is 0. So Rn is the orthogonal complement, Rn is the direct sum of these guys, and so these things are orthogonal complements. Again, not something we'll see till later in this class, but I think you've seen it previously. Similarly, over here, so A transpose goes backwards. Now, these are not inverses. I almost wrote that they were, but A transpose restricted to the column space maps onto the row space bijectively. So this, since A transpose goes this way, this has a null space. And so that is going to be a subspace over here. So this is the null space of A transpose. And for the same reason why these things are orthogonal complements, so are these subspaces, because we just applied to A transpose. So this has dimension. So Rm is the range of A, the column space, the direct sum of the column space with the left null space. And so if this is R dimensional, then this down here is M minus R dimensional. So sometimes we call this the left null space. And the reason why is because if you think now about A transpose, anything that is in the null space of A transpose, let me call this Y. So if this is going to equal the 0 vector, then you can instead think about multiplying Y transpose on the left of A. So in other words, as a row vector here, and this product here is going to be this 1 by n row vector. So vectors in here, the left null space, you can think of as row vectors, such that when you multiply on the left by A, you get the 0 row vectors. So now think about how this is going to relate to linear functions. Remember I said columns are vectors and rows are linear functions. So you can think of this as a linear scalar function that annihilates all of the columns here. So in other words, that annihilates this. Now, as I said that, one of those is in the dual space, one of them is in the space itself, and that's when we abstract this to general linear maps, we can't just say that these subspaces are going to live in the same domain and are going to be orthogonal. That's what happens when you identify the dual space with row vectors. And so this is something that we'll come back to. But again, I think it helps to see the connections between these subspaces for matrices in advance of us doing it more generally for linear maps. Otherwise, you see these results for linear maps, and it's you don't really have any context, or you don't really see what they are generalizing. So again, a lot of you have taken an undergraduate linear algebra course, and you've seen column space and row space. I don't know if you've seen a picture like this, but I think it helps to see how these four things are put together. Let me actually finish this slide by showing you why A is bijective when restricted to the row space. So this is something that we actually have to do after we show that we have these direct sums. So let's assume that. Again, I'm not proving every detail of this. That would take a lot longer. But let's assume that we know that Rn is a direct sum of the row space and the null space. In other words, that's not hard. You could just add up the dimensions, and I already showed you why something in here is orthogonal to something in here. Okay, so assuming this is the case, let's take two vectors. Let's call it x and y in the row space, and let's assume that A maps them to the same thing in the column space. Again, we have to show that. Well, I should say that if we know these things are the same dimension, all we have to do is show that this map is 1 to 1. So let's assume that. So let's say that Ax equals Ay, where x and y are in the row space. And then what does this mean? Then that means that A times x minus y equals 0, and so that means that x minus y is in the null space, because this is something that gets mapped to 0. Now, x minus y is in the null space, but also since x and y are in the row space, then x minus y is in the row space as well. So, and is in the row space. So the fact that it's in both of these, and Rn is a direct sum of these things, means that it has to be the 0 vector. Remember, Rn is a direct sum of two subspaces if they intersect trivially. Okay, so, and the dimensions add up. So in other words, a necessary condition is that they act trivially. And so this means that x minus y has to be in the intersection of those, which is just the 0 vector. And so therefore, that means that x equals y. In other words, A is injective, or 1 to 1, on this subspace. And therefore, because they're the same dimension, it has to be bijective. There are two more things that I want to review from undergraduate linear algebra, just so you think about these concepts in the right way when we do the generalization. The first one is how to multiply matrices. Now we know how to do this, but I want to show you 4 ways to think about this. So let's suppose that, again, A is a linear map from Rn to Rm. Let's suppose that B goes from Rp to Rn. And I'm doing this so when we write things like A times B times X, we can think about X as being in Rp. So X is here, it gets mapped to Bx here, and then it gets mapped to ABx here. Okay, so this is something that is also mentioned in Gil Strang's wonderful book. So we can think about multiplying these matrices rows by columns. Let me show you what I mean by that. So for number 1, let's suppose that we have a matrix A, and so this is A and this is B. And if we have, let's suppose we have row I here times column J here. And then the product of, so this is M, to be careful, yeah, this is M times N, and this is N times P. A good way to remember this, if you get confused, is when you multiply matrices, these inner two numbers have to be the same. So that N has to match that N, and the result is going to be M by P. So the resulting matrix AB is M by P. And this entry right here, which is so the ijth entry means, again, we do the L. So this is I and this is J. So it's the ijth entry. That is the product of this row I with this column J. So I'm going to think of it's this linear scalar function applied to this vector. And so in this way, we can think of Aij, I guess I ran out of room here, but I'll write it here, is Li comma xj. So let me box that just to highlight it. So that's how you think of this as rows by column. This is how we usually actually compute matrices. We think of these things as rows, we think of these as columns, and then we do all of these dot products. However, there are other ways to think about multiply matrices which are useful in some other contexts. So we can do it by columns. That's the second way. And for this, I want you to think about, I might draw this picture a little bit smaller this time. So think of this as A, and think of this as B. And now I want you to think about A as being just a block, like a matrix, and imagine these columns. So this is x1, and this goes up to xp. So now this product you can think of as, so this is m times p, so this is again m of these and p of these. So the p columns you can think of as a times x1 all the way up to a times xp. So in other words, this here is a times x1, and this is a times xp. So again, you can think of this as A times the columns of B. Now, you can do the same thing, but by row. So you can fix B and look at the rows of A. So if you do that, then here is A. Again, I'm drawing this smaller and smaller as I'm going through because I want to make sure that I have room. And this is B. So think about A as, so I'm going to call this one L1 to because I want to think about these things as linear scalar functions, and rows are scalar functions. So the rows of A are, say, L1 up to Lm, and the product here, now what we get is a matrix where this is L1 times B. So the first row is L1B, and then the last row is LMB. Finally, the last way, if you think about what's left, we have rows by columns. So we can do columns of A by rows of B. So for this one, so this is 4. So here we have, again, we have A here, and we have B. So this is A, and this is B. Let me, I don't know what I really want to call the columns of A and the rows of B. But what this ends up being is we get basically a double sum. So every possible column here gets multiplied by every possible row here. Actually, yeah. So I'll call this one A1, and I'll call this A. What's that going to be? AN, and then I'll call this one. I'll call this B. One. Let me call that B1 transpose to emphasize the fact that it's a row vector, even though I didn't do that over here. I think it's fine. B1, and then up to B. Bn transpose here. So now I'm taking all possible, let me do ij equals 1 up to n. So I'm taking all possible i's and j's from 1 up to n. So this is really a double sum. I just don't like to write double sums if I can help it. And this is going to be ai times bj transpose. And if you think about what that is this is going to be a rank 1 m by p matrix. And again, I'm not going into detail. I'm not justifying this, but I want you to realize that if you take let's do an example of this. Let me take a 1, 2, 3 times x, y. Let me take a row vector times a column vector. And if you do this, notice what you get. You get x, y, 2x, 2y, 3x, and 3y. So this is a rank 1. So all of the columns and rows are multiples of each other. This is a rank 1 matrix. And so you have a sum of n squared rank 1 matrices. This is probably the least useful of these, but there are applications when it helps to think about things like this, and it is the fourth and final way to multiply matrices. And I think it helps to see these things all together and to think about them in terms of row vectors and column vectors, especially when we move on later to talk about generalize this and we think about row vectors as linear functions and column vectors as actual vectors. Finally, we will finish this lecture with a quick review of systems of equations and Gaussian elimination. It's not going to be as much that I'm going to teach you how to do this. It's just I'm going to review how to do this. I assume you all know, and I want you to think about how these vectors relate to the 4 subspaces that we have seen. So this is just a refresher, and I'll go fairly quickly because of that. Here is the 4x4 system that we will solve. So there's a lot of ways to proceed from here, but I think what we will do is what makes the most sense is to use equation 1 and subtract suitable copies from it to eliminate x1 in the other equations. So if we subtract equation 1 from equation 2, variable by variable or term by term, we get x2 plus x3 minus 2x4 equals u2 minus u1. Now we need to subtract 2 copies of this from equation 3, and if we do that, then we get negative x2, then we get minus 2x3, and then minus 3x4 equals u3 minus 2u1. Finally, if we subtract 3 copies of this first equation from the last one, the x1s cancel, then we get x2, and luckily the x3s happen to cancel. 3 times this, or 6x3 minus 6x3, and then we get 2 of these minus 9 of these, so that's minus 7x4 equals u4 minus 3u1. Okay, so now from here we will use the first equation to eliminate x2 in these next 2 equations. So if we do that, so to eliminate, I guess we add equation 1 to equation 2, and then we subtract equation 1 from equation 3. So let's do that. So if we start with equation 2 and we add equation 1, we get minus x3. It's so easy to mess this up, to mess up a sign. So fortunately I have an edit, and if I make a mistake, I'll go back and do it again. But let's see how many tries it takes. Okay, so we're adding this to that. So that's going to give us a minus 5x4. And now let's see what we get. We're adding up these 4 terms. So we get u3, we get positive u2, I think. Yep, I see a u2 there. And now we get minus 3u1. Okay, now we're going to subtract this equation 1 from equation 3. The u2's cancel. We get minus 7 minus negative 2, so that's going to be minus 5. Oh, I almost forgot my x3. 0x3 minus x3, so that's going to be minus x3. And now we have negative 7 minus negative 2, so that's minus 5 x4. And now here we get u4. We're subtracting a u2. And now we have -3 minus -1 is minus 2u1. Okay, so here's what we have. Now we can set this up so there's a non-trivial solution. Or at least I should say I found this exercise. I didn't make this one up. I found this somewhere. It has a non-trivial solution. So if we now subtract these things, so let's subtract. So let's take this equation and subtract that. And if we do that, the left-hand side is going to become 0, and the right-hand side is u4 minus u3. And then we have minus u2 minus another u2, so that's minus 2u2. And then we have, gotta be careful here, minus 2 minus -3, which is plus u1. Okay, so any solution that satisfies this is going to have to, any solution u1, u2, u3, u4 is going to have to satisfy this equation here. And we can think of this equation as like a dot product, one. So now I'm going to read right to left. So u1, u2, u3, u4. So 1, -2, -3. Sorry, not -3. -1, and then 1 times u1, u2, u3, u4. So we're not saying that any solution x1, x2, x3, I mean, so these u's are unknown as well. So any u1, u2, u3, u4 in the target space that admits such a solution here has to satisfy this equation. And we can think of this thing here as L. Now at this point, let's think about where these vectors live in relation to our 4 subspaces. So let me draw this up here. So we have R4. So A goes from R4 to R4. And here are our 4 subspaces. So this is the range of A transpose. This is the row space. And then the null space is down here. And then up here, we have the column space, the range of A. And down here we have the null space of A transpose. Okay, so this vector u lives, well, if there's a solution, that means that this vector u lives in the range. It's some vector over here that gets hit from some, so x1, x2, x3, x4 is something that lives in x4. It might live, we don't know what, so let me draw that. So I don't know, x is going to be some, since this is the direct product, is going to be, or direct sum, it can be written uniquely as something in here and something in there. So x gets mapped somewhere over here. So this is, so u, this is u right here. And now, what about this L? So L is something that is orthogonal or perpendicular to u, so that's going to live in this left null space. So L is this vector, lives in here. And the fact that it lives in there means that if we take, actually, how about if I do this first? Let me take this matrix and write it down here. Or let me write this in matrix form. So that's going to be 1, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3, 3, 4, 6, 2. So this is A, then X is X1, X2, X3, X4. And then U is U1, U2, U3, U4. Okay, so if there's a solution if and only if, or this is a solution if and only if it is orthogonal to this vector here. And so you can think of that vector, again, because it lives in the left null space, it has the property that if you multiply it on the left of A, 1, negative 2, negative 1, 1, then this thing is just going to be the 0 row vector, 0, 0, 0, 0. And you can check that, indeed, this linear combination of the rows is going to be 0. In other words, if you take, so let me make this a little clearer. My pen was not perfect on me back then. So if I take one of these, if I take negative 2 of these, if I take negative 1 of these, and I negative 1, and I take one of these, I mean, I'm literally taking this linear combination of these rows, you can check and get 0, 0, 0, and oh, I get this vector right here. And this is something, so let's write this out algebraically. So what we have is, let me switch my pen back. So we have mx equals u and lu equals 0. Now I'm going to think of this instead of as a scalar approximation, just as a row vector times a column vector. And so if we have both of these things, then it better be so L times U is 0. This thing here is U. So if I multiply L on the left, if L M X, so again, this is a row vector, a matrix, and then a column vector. So L M X must be equal to L U, again, because that is U, which is 0, and this holds for all x in R4, then it must be the case that LM equals 0. In other words, this is the algebraic reason why this has to hold. And this is the picture that I think it's helpful to have in your mind. Okay, so that's the end. That's all I wanted to say about this. Again, if this should not be the first time that you see Gaussian elimination. This should be a review of Gaussian elimination in the context of these 4 subspaces. And you should have these subspaces in your mind as we generalize the notion of both the transpose and then of, I don't want to say generalize, but given a linear map, when you pick a basis, what does the matrix actually represent? So keep this picture in mind for the next few lectures and stay with us.